Okay, so we can begin now. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We have Professor David Delepine from Mexico, and he's going to talk about neutrino resonance spin flavor precision of GeV-Scale astrophysical transient.
Thanks a lot. So it's a pleasure for me to be with you today. I will speak about a work that we did in the beginning of this year about resonance spin flavor with neutrino. So let's go very quickly on the general outline of this talk. So just to record the motivation of the work, to describe the theoretical framework, then to apply to the solar neutrino and to supernova neutrino case, and then some detection prospect in a close future. So the main problems here is that since we know that a neutrino oscillated, we know that they have a mass. So the question is, are there Dirac fermion or Majorana particles? So Majorana to be their own antiparticles. So we need to have these the standard probes, the smoking gun, is neutrinoless double beta decay, which is sensitive to absolute mass. So it's a very sensitive and very difficult experiment. So one alternative way is to use the neutrino electromagnetic properties. And one of them is the possibility to have a non-zero magnetic moment, which means that we could have some resonance spin flavor precession. So this means that active left-handed neutrino can be transformed into a right-handed state through the effect of interaction with magnetic astrophysical fields. So what happened for the Dirac case? In the Dirac case, it converts to a sterile right-handed neutrino, so the flux really disappears. In the Majorana case, it converts to active antineutrino, so the flux is preserved, but helicity will change that it can induce in the detection modification in the angular distribution. So there is two main constraints on this model. One is the tight constraint on neutrino magnetic moment coming from Borexino that has to be smaller than 10⁻11 Bohr magneton. And the other one is coming from the cooling bond from supernova observation SN 1987A, which is strongly constrains the transformation of left-handed neutrino to right-handed neutrino in the core of the supernova. So the question here is to go to see if there is still some windows to look for the effect of resonance spin flavor precession to be useful to distinguish between direct and Majorana fermions, and if nothing is seen, in case of a null result, to be able to put a limit on the neutrino magnetic moment. So before to go to the formally, there is one important point here to mention that when we are speaking about the resonant spin flavor precession, we need that this quantity omega-3 to be close to 0. So with this relation, if we want to get a place for the place where the resonance is taking place is related to the delta m square over E nu. So it means that if we are increasing the energy of the neutrino, we need to go to a part of the star with a lower density to have this resonance. So in the case of the sun, for neutrino of 10 MeV, the resonance is taking place in the radiative core. So what we will try to do is to look for neutrino of 1 GeV, which is typically the energy of a solar flare neutrino, when the resonance is at the tachocline, which is very good because the tachocline zone of the sun are quite a strong toroidal magnetic field. For the supernova, it's quite different because the supernova for 10 MeV, the resonance will take place in the stellar envelope, well outside the cooling region. So we can avoid this the constraint coming from SN 1987A. And for the case of 1 GeV supernova neutrino, when it's in the dilute stellar wind, and in that case, essentially, the LCT is frozen. The magnetic field is too low to generate resonant spin flavor precession. So we can use it as a standard candle to limit, to avoid the uncertainties on some astrophysical uncertainties. So let's go to be quite fast on the formalism, because the formalism we use is the standard formalism for open quantum system. So we use the Lindblad master equation. And here we put the effective Hamiltonian completely with the vacuum part, the matter effect, and the magnetic one. And the new is coming from a thermal effect of neutrino diffusion. This point we didn't take into account in our analysis. So, and the D term, this is a dissipator that is inducing the decoherence due to collision and to the turbulence of magnetic hydrodynamics. So from this Lindblad master equation, we can get the generalized block equation that will describe the LCT variation, and the diagonal part is given by what we call it before omega 3, and the non-diagonal part will be proportional to the magnetic field and the magnetic moment of the neutrino. And gamma will describe the depolarization from turbulence due to decoherence effect. The main parameters here is the gamma parameter that will describe the adiabaticity of the resonance. So if gamma is much larger than 1, we are in the full adiabatic regime. It means that we will have a complete flip from LCT, from -1, from left-handed to +1 in a very efficient way. If gamma is much smaller than 1, essentially the LCT is frozen. So what we have to look now is in the case of solar or supernova, we have to look if we can find some region of the star where the adiabatic regime is still useful for the energy of the neutrino that we want to look for. So let's go first to the solar flare neutrino. So the solar flare neutrino, they are produced for proton interacting with chromosphere plasma, producing pions, and these pions decaying in a neutrino. The neutrino energy can go to a few GeV. They have a power law spectrum, relatively well known, but under studies. And the fluence at Earth is not so small. Of course, it's much smaller than other source of neutrino, but it's around between 200 to 800 neutrino per centimeter square above 100 MeV. So maybe one question that you can ask me is if these neutrinos are produced in the chromosphere, how they are, how they could, if this resonant spin flavor precession to reach the Earth. Of course, what we are interested is the neutrinos that are produced on the opposite side of the sun. So, as we know very well, the neutrino interact very low with matter. So it means that for them, the sun is practically transparent. So this neutrino produced on the opposite side to go to the Earth, they will pass through the sun and through the different zone region of the sun, the radiative zone, also the tachocline, and the convective zone. So for the sun, we use a traditional model for the magnetic field. In the radiative zone, we use the Wood-Saxon model for the magnetic field. And for the tachocline, we use the Gaussian tachocline peak that, according to the models, they can reach between 20 and 50 kilogauss. Which is very nice, because if we remember the resonant condition, in fact, for 1 GeV neutrino, the resonance is just on the tachocline zone. So with this strong magnetic field, we can have a very efficient, very efficient, we'll see in the details a little later, but we could have an efficient transition, change in helicity in that region, depending on the magnetic moment, of course. Then we have the convective zone. In the convective zone, the effect of the magnetic field is due to this turbulence effect. So let's have a look on how the change in helicity are depending on the magnetic moment. So in the case of the solar flare neutrino, but it's very depending on that, because if we are just using the Borexino limit, assuming that the magnetic moment is just below, then we can have a strong, highly adiabatic regime, and this is the blue curve, and we can get a change in helicity from -1 to essentially to 0. It's not to -1, but it's enough, big enough to generate some observable effect. But if we go to magnetic moments up to 10⁻11, or a little smaller than 10⁻11, then we reach already the non-adiabatic regime. So essentially, the helicity is not modified, or is very, the modification is very small, so it could be very difficult to observe in detection on Earth. Yeah. The convective zone is just we can see the effect of the turbulence magnetic field just as a small perturbation. It will not change really the prediction. It acts more like a noise, essentially. So this is the same curve, but in that case, solving completely the equation using the model, the sun magnetic field models. So, and it confirms what we said before. In fact, if you assume the magnetic moment to be at the Borexino limit, we can get from -1 to -0.13. So we have a significant spin flavor conversion that we can give some effect, observable effect in detection. But of course, we see that if mu is going to 10⁻12, the effect is strongly suppressed. So there is two points. If the magnetic field is between 10⁻12 and 10⁻11, so we can get some effect. If we don't see them, it means that the magnetic moment should be smaller than that. In the case of the solar flare neutrino. For the supernova, the situation is much better because in that case, the resonance is taking place in the outside envelope of the star, so beyond the cooling core of the supernova. So we can avoid this strong limit. You could ask me why the density resonance is so large compared to the solar case, but it's due because here the delta m square that is playing is not delta m square 1, 2, but it's delta m square 1, 3. It's why we can, the resonance energy is between 10 to 3, 10 to 4, which is like 2 orders of magnitude bigger than in the case of the Sun, but in the case of the Sun, what is the relevant delta M square is delta M square 1, 2. So for the magnetic field, according to the supernova model, it can be as large as 10 to 6 to 10 to 8. So it means that the adiabatic parameter, the gamma, is much larger than 1, which means essentially that much larger than 1, of course, for a magnetic moment of around 10 minus 12. So we can have practically a complete helicity inversion. It can be very efficient. So it means that if the neutrinos are Dirac fermions, we will have a complete transformation of left-handed neutrino to right-handed neutrino, so the flux will disappear. In the case of the Majorana, the flux will be preserved, but as the helicity is changing, the angular distribution, if we can measure the angular distribution in the detector, then we will see a difference compared to the strict standard model case with left-handed, only left-handed neutrino. So in that case, well, it's important to mention that for 1 GeV, the resonance is in the dilute stellar wind. So assuming that the magnetic field is behaving like a dipole, it means that essentially it's going like 1 over r to the cube. So at this, in that region, essentially is going to 0. So the adiabaticity is collapsing, and gamma is going to 0. So this 1 GeV neutrino will not, the resonance spin flavor precession is not efficient at all for them, so they will not change. So we can use them as a standard candle. Which is important here to mention that the production of the non-thermal 1 GeV neutrino is not exactly the same that the thermal burst, of course. It's a production very similar to the case of the solar flare neutrino. So it's an interaction between the ejecta matter with stellar medium interaction that will produce collision between protons and producing pion that will decay in neutrino. But both process, the thermal burst and non-thermal tail, they first are produced essentially at the same place, at the supernova place. And the second point is that they are depending, both of them, on the total energy of the burst. So if we could have this non-thermal tail as a standard candle to limit the uncertainties on the distance of the supernova and also on the uncertainties on how to measure the total energy of the burst. But we have to keep in mind that we have still some uncertainties coming from the models to describe how to produce these non-thermal tails. Tail neutrinos. So here essentially we can see in the graph below that if we can, the interesting point is that to lose the adiabaticity limit, we need to go to a magnetic moment of the neutrino to be around 10 minus 13, 10 minus 14. So it means that in the case of the supernova, we could have access to a magnetic moment up to 10 minus 13, 10 minus 14, which is 1 order of magnitude bigger than the case of the Sun, for instance. So as I told you, if we define the ratio R as the number of events induced by the thermal burst neutrino of 10 MeV about the thermal, about the event induced by the GeV neutrino produced at the supernova, then we have essentially two cancellation or in the astrophysical uncertainties, one about the distance and the other one about the total explosion energy. still, it's not completely independent of the supernova modeling, as we need to have a model to generate this thermal burst neutrino and also the non-thermal tail neutrino. So I say that in the case of the resonance spin flavor precision can be very efficient for the electronic neutrino. So the electronic neutrino will completely change from left-handed to right-handed, but the burst will produce all flavor. So it's why, in fact, in Earth we expect a deficit of about 25, about 30% in the case of direct neutrino, due to the fact that the flux is essentially 1/3 of the neutrino are produced as electronic neutrino essentially. So what we can say is that if R is much smaller than the standard model expectation for this ratio, then it will favor the Dirac fermions for the neutrino, and with with magnetic moments bigger than 10⁻14. In the case, if R is essentially is the same order of the standard model one, it will favor Majorana case. And what will be very important is to see if we can have access to the angular distribution in the detection, because it's where we could see the difference between standard model with magnetic moments for neutrino or without magnetic moments, no? Because with magnetic moments, if we see an angular distribution compatible with the Helicity transformation, it will be an indication of Majorana fermion with magnetic moment for the neutrino. And essentially, we will give some more details a little later, but we can expect a deficit about 15% in the detector, induced by this change of 25–30% in the flux of neutrino reaching the Earth. So essentially, as we already said, if we see nothing, it means that we could use that to put a limit on the magnetic moments. So, for instance, in the case of the sun, if we need to have an asymmetry bigger than 10% to be able to see to see it in the detector. So it means that in that case, if the magnetic field, the tachocline zone is around 50 kilogauss, that the magnetic moment has to be bigger than 10⁻12. So if we don't see any signal in the detection, it means that we need this magnetic moment to be smaller than 10⁻12. Of course, it's depending of the magnetic field, but essentially it's the magnetic field in the tachocline, as we said, is between 20 and 50 kilogauss. So the change is not so strong. In the case of the supernova, if we don't see any effect on in the detection, then we could improve even better the limit on the magnetic moment. We could reach like 10⁻13, 10⁻14 Bohr magneton for the magnetic moment of the neutrino. Which is very competitive compared to the experimental expectation to construct this one. So just to give you some very close numerical value, I mean the really the important one is this table to give an idea about the signal that can be seen in a coherent elastic neutrino.
We have 5 minutes left.
Okay, very good. I'm close to conclude. So you see that in the coherent elastic neutrino nucleus scattering, it's the more promising effect because it's much larger than in electron neutrino asymmetry, and of course it can be as it depends on the magnetic moment, but we can reach quite 10% or up to 43% of deficit. And so let's go quickly to say about what are the experimental outlook. So of course we need to localize one activity of the sun to be able to be alerted when these neutrinos are produced. So we need a collaboration with different detector based on other signal like AUC, it's gamma ray alerts or X-ray triggers. And for the supernova, the same way we need to be to know when we have a supernova burst to be able to look for to select the events coming from these events. So we really need a collaboration between these different experiments to improve our knowledge on the neutrino magnetic moments. So, and the question if it's possible to get it, yes, we can get, because if we have an asymmetry, but essentially the number of events is going like 1 over a square. So to measure an asymmetry of 14%, we need like 50 events. So with what we know about the flux of this neutrino, that in fact hypercamioncandy and ice cube generation 2 can do it for galactic supernova. In fact, there is already some work done in that direction. So we have some ice cube solar flare search that putting some need on GeV flare fluence. SuperK also we're searching for neutrino produced by solar flare, and they put it some constraint on the flux. It's work of 2023-24, and about the coherent electric scattering, that with the Conus Plus we could expect to reach sub 10% uncertainties could be reached quite very soon. So in that sense, we can say we say that it's not completely out of experimental scope what we are speaking about. And so in summary, that this is essentially the main result. I mean, for the solar flare neutrino of 1 GeV, the resonance is taking place in the tachyc line. So we can have some adiabatic resonance spin favor precession that with 14% in neutrino electron scattering and up to 44% of deficit in the case of coherent elastic neutrino nuclear scattering. Of course, it depends on the magnetic moment of the neutrino. This is using the Braggsino limit for mu nu, of course. And in the case of the supernova, essentially with 10 MeV, we can avoid the bond on cooling, and the deficit is a little less, but we can it's sensitive to mu nu up to 10 minus 40. And the deficit in the coherent elastic neutrino scattering is around 18%. And we can use the supernova GeV-Scale as a standard candle to limit the effect of uncertainties, astrophysical uncertainties that usually are very large for supernova clips. So, and the last point that I want to emphasize, if we don't see anything, so it means that we can use this result to put a limit on the magnetic moments and improve an improvement of 1 or 2 orders of magnitude compared to actual bonds on mu. So this is my conclusion. I want to thank you a lot to listen me, and please, I'm for